Welcome, everyone. Today is, we're going to move on to linked lists. Yesterday, we only went through 5 of the questions in the first chapter. You're like, Jay, shouldn't you finish out that chapter? And I'm like, no. Those final 5 questions are so hard. And what I tend to do, and this is a good strategy, especially if this is your first time prepping for a technical interview, is to really only go through the first 4 or 5 questions before moving on to the next chapter. And then coming back to tackle those harder ones when you're done. For some, the first 4 or 5 questions may be really tough in the first place, but also I like to warm up a bit before I throw myself in the deep end. So that's what we're doing here. Now, today we're going to be talking about linked lists, and I'm excited about it for 2 reasons, neither of which are their real-world use cases. I'll get really excited about trees and graphs when we get to real-world use cases, but today, what I really like about linked lists is that it forces you to do 2 different things. One, it really forces you to diagram, which is my favorite technique for approaching algorithms, and I'll talk about that soon. The second thing is that it forces you in JavaScript to use structures to represent data structures. What do I mean by that? Well, if you'll take a look at linked lists on page 92 in Cracking the Coding Interview, what you'll find is that she starts using classes in Java, these are Java classes, to create these nodes and to append functions to the class, right? The methods, rather. And this is something you could do in JavaScript as well. We have the syntactic sugar for it, class syntax. Been around for long enough that it's almost not even sugar anymore, right? I recommend also, if you want to push your boundaries of JavaScript knowledge, to try building these data structures without classes and with classes. For without classes, check out prototypes. You can go to javascript.info. And actually, let me do that for you real quick so you know what that looks like. This is probably my favorite channel. Oh, I already got a bunch of stuff here. Favorite website for learning more about JavaScript. Let's go into javascript.info. And essentially, it's just a bunch of really great things on everything about JavaScript syntax, right? And here's the one I'm kind of looking at, prototypal inheritance. Sometimes people want you to know that. You also have class basic syntax, class inheritance, static properties and methods. If you're not familiar with class syntax, check it out here or someone else's YouTube video. Oh, I'm getting a connection unstable. Okay, connection unstable went away. I'll just repeat myself. Check out these 2 things, prototypes, inheritance, and classes, especially if you've done neither of them before, but especially if you're a little fuzzy on either of them. They're really great, and there's tons of ways of building these objects out in JavaScript. Now, I'm going to use classes just to keep it simple, and that's how I'd probably do it in an interview, but seriously, practice other ways. It'd be really, really fantastic for you. Okay. So that's one thing I'm excited about. The second thing is diagramming. Diagramming is a very useful technique where you sort of draw out what's happening to help you understand it and to help you problem solve with it. You basically can't do linked lists without diagramming because it's just what you'll see, it's super visual. That's all the spiel I had for today. I can't wait till we get to more like real world data structures. People use linked lists in the real world. But let me tell you, not in the JavaScript world. Even like I've actually not gotten a single question on linked lists in an interview. Now, you may, so prepare for them. And frankly, it prepares you super well for the rest of the chapter. So follow along and we'll do good. I am going to go ahead and share my iPad. Let's get that rolling. And here we go. Perfect. Okay, there we go. Okay, so linked lists. I have to teach it visually because it's such a visual thing. So you get to see me diagram. Now, when I diagram, it's pretty terrible, and it doesn't have to be that beautiful or anything at all. Now, you probably see this in the book. right? You see a bunch of boxes and you see some arrows, right? And that represents the connectedness, the linkedness of linked lists. A linked list is basically a node that has a next and sometimes a previous, right? The previous, I can't remember if it's always there or not. I guess we'll see when we dive deeper into it. Oh no, there's a singly linked list where there's no, where there's none of the arrows, and it can only go down, right? You're thinking, well, that's insane. Why would you ever do that? And linked lists are actually one of the primitive foundational data structures to a lot of other data structures. Hash maps can use them, graphs can use them, stacks, anything. Like if we were in C++ land, I'd be like, you better learn linked lists because this stuff is real good. Or I don't know if it's real good, but there's some real good questions that get asked when you're a C++ programmer with this. Usually have to do with pointers, but we don't have to deal with that. So, okay, so this is vaguely what it looks like, right? I'm gonna add those arrows back in. And let's give syntax life to this, okay? So what would I do here? Well, what I wanna represent itself is the node itself. And let's say the node has some data. So when you initialize it, we'll add this to the constructor. I hope I'm doing this right. We'll add this to the constructor. Actually, you know what? Why am I doing this here? Let's do this on an actual, REPL. We'll do this on Chrome DevTools real quick. All right. Okay, so for reals this time. All right, so class node, and we're going to, let me get rid of Grammarly. Let me get rid of that. I was kind of interviewing with them, and then I decided to add their extension, and now I regret adding their extension. Get out of here. Settings, quit Grammarly. Thank you. Okay, cool. Constructor, let's say val, right? We'll just call it val. And then we'll say this dot val equals val. Cool. So, you know, it has some data attached to it. Typically, nodes always do this, right? They always have some data. You'll see that when we do graphs and such. But there's another thing to it. And I'm just going to follow the book almost verbatim. Pen to tell val. What she does is, oh, how does she do this? I think it's something like it creates a new node. Let's see if we can do that in JavaScript. So const new node equals new node with val. Let's see if that works at all. Actually, I'm going to start with that just to see. A equals new node 1. A dot append to tell 2. A. What is A? A has, yeah, and you have this node object, and okay, it passed. I didn't have that actually do anything. All right, so we're all discovering classes while we teach something that uses classes. Awesome. So new node equals new node with a val, and then it does this thing while. Oh, now we need to get this. So this dot next equals new node, right? I think that's all we do for the JavaScript version. Let's see if that works. Let's do this again. So A equals new node 1, A dot append to tail 2, A, and let's check that out. Yeah, nice. Now look at this. This is very nice. And this is why I like doing it in the Chrome DevTools. You have this object you've created, and it has a next. So next and previous come up a lot when you're dealing with these things because it is, you know, there is a next node. And when you're at the next node, the previous node is this node, right? Now, this is a singly linked list. So that means the next node here has a value of 2, right? Because that's the one that we appended to the tail. And then we were off to the races. So if I were to append to that tail, I could say a.next, and that grabs the next node. I could say append to tail 3. right? But I've done something wrong here. And I hope you'll notice that the fact that, this works, this is cool, but append to tail is supposed to append to the tail of the linked list. It's not supposed to append to, it's not supposed to be like if I do a.append to tail 4, now I have, right? My next node is 4, right? And that makes sense if you look at my code, but the spirit of this function is supposed to be different. It's supposed to say, okay, let's go ahead and redo it. It's not supposed to say this. It's supposed to say while this dot next, right? So while we have a next, we can do, actually, let's store the value of this. So let current node equal this, okay? And if you don't know what this is, frankly, pause right now, go to javascript.info, figure out what this is. But essentially, it's a reference to the current instance of node that is being referenced in the execution context here. That's the important word, is execution context. And you want to know that for interviews. So seriously, pause, figure that out, come back. I'll be here. All right, so current node equals this. So while, let's do current node dot next. Okay, cool. So while current node dot next, node equals current node dot next. What is that going to do? That's a fun little thing where it's going to go all the way until there is no next node, and whatever that is, then we're at the very tail end of this thing, right? Equals new node. Cool. Look at that. Let's see this work. Okay, so a equals new node 1, right? A dot append to tail 2. I hope this works because I'm doing it live, right? A dot append to tail 3. A dot append to tail 4. Let's stop there. Okay, A. So let's check it. Now, if we did this right, the next node should be, yes, look at that, value 2, right? So the next node has a value 2. Its next node has a value of 3. And its next node has a value of 4, and then we are done, right? So that is what appending to the tail is, right? And so that's pretty useful there, right? Now, this isn't the only way to write a linked list structure. You can have your linked list do whatever you want. You can also have a previous, a next. You can do all sorts of stuff with it, and we're actually going to dive into those things during this, during all of our questions here. Now, this book goes into deleting a node from a singly linked list, and I want to show visually what that would have to look like. So I'm going to stop sharing my screen. We're going to go over to my iPad again, and I'm going to show you what that looks like. If I can find my iPad. All right, pulling it up. All right, we're back in town. Let's come back. There we go. A little bit of coffee. Okay, so let's delete some of this. Now, let's say, funny, I need to delete things. Anyway, so let's say we have this linked list, right? Let's do the same exact one. It had 4 nodes to it, right? 1, 2, 3, and 4 were their values. And now we need to delete from this linked list. Now, you might think, like, if this were a hash map, right? Say if we had like node A, it had value 1, or it had an let's delete that. Let's make a stupid, simple linked list like B2, C3, D4, right? And this is just not representative. But essentially, if you want to delete something from here, you could just say, like, if this was A, you could be like delete A at C, and you would be done. The object would still survive. If you just came in here and deleted number 3 over here, just removed it, 4 is now orphaned. It's now all alone. 2 is pointing to nothing, right? And so now you've deleted too much of the linked list. And that's the trick with these, right? And so you don't want that to happen, essentially. You want to say that 2 is now connected to 4. And that's actually somewhat of a, no, I wouldn't say it's a simpler approach, but it's simple enough to do. So how would you do that? Well, let's take a look again at this and we'll diagram it out. So how do I diagram these things out, right? And this is in general something that, a technique that I really want you to pay attention to, because so often in algorithms and data structures, we're iterating through stuff. We are looping through things. We're taking the next node until there isn't a next node, right? And so here for deleting it, we have something important to do. We have to start right here at 1. And frankly, in these linked list questions, you don't get to start at 2 and contain a reference of it. You have to, or start at 3 and contain a reference of it. You saw the data structure. The only way to access 2, 3, 4 was to start at A and be like dot next, dot next, dot next, right? That's the only way you could access those linked lists. That's the trick to them. That's why they're tricky, rather, right? And so that's what you have to pay attention to when you're doing this, right? So how do we iterate through these things? Well, we saw it earlier. We just had that while loop where we're like, okay, well, A dot next, well, keep going, right? And so let's say we wanted to delete number 3 over here. Well, then what do we do? Well, let's start with, let's say we have this function to delete it. And I'm trying to remember, I'm actually looking in the book a little bit right now because it's a little fuzzy to me as well. But let's say you started here. Let's use I as our, usually when we do a for loop, we use I. We're not for looping here, but I'll use that to keep track. So actually, let's not. Let's do a color. Let's do a color. So say we're here. All right, and then we're like, we want to delete number 3. Well, is the value 3? No, it's not. Okay, let's go to the next one. Like, oh, the value is 2. Well, we know the next one's 3, but we're not supposed to know that, right? So let's keep going. And then we come over to here to 3. And we're like, oh, we're in 3 here. Oh, nice, nice. Okay, so this is what we want to delete. Cool. So here's the problem. We need to connect this guy with this guy, but we don't have a reference to this guy. Right, we lost that when we said A dot next. You would have to go all the way back to A and be like dot next until you reached the value right before it. So what do we do there? We keep track of the previous one, right? That's all you do. So you're keeping track. In the book, they call it the head. So we hit. We're like at the head, and then we say something like. Node dot next, A dot next. And we're like, okay, so the head is 2, right? A dot next is 3. Do you see how I came to that? So we're here at 2. I'm sorry, we're here at 3, right? Or I'm so sorry. The caffeine has not fully hit in yet. So we're here at 2. I promise this time. And the head is now 2 because that's where we are. We're here at the head. The next one is 3, A dot next. That's how we're accessing it, right? And we're like, oh, okay, well, the next one is the one we're looking for. Now we can hang on to this head, right? We can hang on to our head. That's funny. And then we could just say A dot, or we could say, so if this is A dot next, then A dot next is 4. And what do we want to do there? Well, we want to say head dot next equals this 4 one here. We want to say head dot next equals A dot next dot next. What is that going to do? That is going to say 2 is no longer connected. Take a look up here at the diagram. 2 is no longer connected to 3. 3 is still connected to 4. That's interesting. But 2 is now connected to 4. And 3 has nothing referencing it at all. Right, so it can't be accessed. It's been deleted from the list. Now, while 3 is hanging on to this little 4 over here, it's actually going to be garbage collected at some point. It's going to get out of here, and that's going to be garbage collected because there's no more references to it. It doesn't have anything to keep it from being garbage collected. So it's trash. And then we have our connection from 2 to 4. So we deleted it. Very cool. So that's how we delete things in linked lists. And that's a super important thing to start thinking in linked lists, right? So what's the next thing? The next thing is the runner technique. What is the runner technique? So this is where you iterate through a linked list. Let's say you have this big linked list, right? And where the runner technique really comes into play is when you're trying to figure something out about this linked list. Now, what are we trying to figure out? I'm going to do this little ridiculous 3D, it's 2D drawing, but I mean, you know, really it's still next, right, is what I'm trying to say. And sorry about that. There we go. And I'm going to introduce a loop in the linked list, right? So this is like .next, 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 and now we're stuck in a loop, right? This thing is going to go on forever. You will never run out of, if you did a pen to tail on this thing, you would probably crash your browser or it would run into some sort of error. Hopefully it would run into an error, right? But if you had less guardrails, you would certainly crash your computer, you know, because it's just going to do that infinitely, right? So how do we detect these infinite loops, right? When you're having linked lists? Well, that is a great question, and that is what the runner technique tries to solve. And these are one of the top questions we'll be asked when we start doing the actual questions, right? So let's talk about it for a second, right? Because this is another great way to just diagram stuff as well. And I'm going to use 2 colors here. I'm going to delete this up here. Get out of here. I don't want to see it. And essentially, we're going to have 2 iterators. Two. So we talked about iterating. Iterating is going through each item, sometimes in a loop. There's a series of items, though, and you say, oh, I'm iterating through them. You're going through them, right? It's technical speak. So we have 2 iterators here. I'm going to go red. I'm going to go purple. You can hardly tell that's purple, but that's fine. So you have red and you have purple. Now, the runner technique is where one of these pointers goes faster than the other pointer. What does faster mean? Well, fortunately, we can have a nice, concise technical definition of faster here. Red increments by 1. Purple increments by 2. Look at that. So you'd say a dot next here. You'd say a dot next here. And that's really all there is to it. So what does that give us, right? Well, let me diagram that out because it's going to make a whole lot more sense when I draw it out. So red only goes by 1. So let's iterate. So first iteration, red is here. Purple is here because it went up 2, right? Next iteration, red is here. Purple is here, down here. You know what? Let me start over and draw numbers in the colors so that makes a little bit more obvious sense and you don't get lost. So here's 1. Here's 1 iteration for purple. Cool. Now let's do it again. This is where red is the second time. Purple is here the second time, right? A dot next. So red is now here second time. Purple is now back here. Look at that. It looped. It's here. Isn't that interesting, right? So next up, we have red is here for 4. And what's purple going to be? It's going to be next. It's here for 4. Oh my God. And now what happened? They're on the same tile. However, red has been the slower one, right? So it should never meet up. If it is if it is a non-looping linked list, they should never run into each other, ever. Purple should always be ahead by miles, but here they are meeting up. That tells us there is a loop and we should stop, right? So that is the runner technique, right? How would we do that in code? Yeah, we'll get to that when we do some of the problems here. Yeah, and she will be asking those problems. Now, there's a little line also where about recursive problems in this chapter. She says, hey, you know, if you're having trouble with a linked list problem, try recursion. That's like, if you're having a hard time, give yourself a harder time. We'll learn recursion later, right? And there actually, I would not recommend recursion in linked lists for us, mere web developers. Recursion in the real world isn't asked quite as much. And when we go over recursion, I do have a really great technique for solving recursive problems. However, we tend to only get asked a few recursive problems in the real world. So we'll cover that when we get there, but don't worry about that line here. I've never used it. And frankly, I haven't even been asked linked list questions in an interview, but they are fantastic practice. So stick along with me. All right, so let's start diving into code. I'm sorry, start diving into questions. I'm actually going to take a 5-minute break because that was a lot of teaching. So the time right now is 9:26 CST AM for me. Hello, everybody from around the world. And I'm going to get back in 5 minutes. It's 9:27, so that's 8, 9, 3. That's 9:33 AM. So mark 5 minutes. I'm going to pause the recording and we'll get back soon. All right, we are back. I highly recommend, by the way, taking like 5-minute breaks every 30 minutes so that your brain doesn't fry and it keeps your body moving, right? We sit a lot. You should take breaks often and walk around. Tyzoid had a question. When you go from A to B to C to D to A to B to D, in other words, you've deleted C. And how do you inform holders of C that it has been removed? You do not. So essentially what happens is B is connected to D now. And so you have effectively removed it without necessarily deleting it from memory, right? So it just does not exist. It is now, it's almost like you've informed B that it's connected to D now. And that's it. And so effectively C doesn't exist. So that's the trick there. All right, we're going to dive into some questions. Let's do this. I'm going to get through as many as I can. We'll see what happens. Oh, it looks like loop detection was the very last question. We might be able to fly through this. We'll see. Let me share my screen. All right. Okay, very cool, very cool, very cool. So we are going to start with question 2.1, and it is called remove dupes. Very fun. Remove dupes, duplicates. So it says, write code to remove duplicates from an unsorted linked list. Interesting. And then a follow-up question that I might not approach. We'll see. How would you solve this problem if a temporary buffer is not allowed? Ooh, I actually have some ideas on that. So let's draw a diagram. We have a linked list with dupes. It did not say if it is a singly or doubly linked list. So what do we do there? Well, in a real world interview, we would just ask them, oh, is it a singly linked list or is it a doubly linked list? That's when the previous thing is added there. I'm going to assume doubly linked list just for fun, right? Just because it's going to be easier on me. But you know, you might be able to look at. They have some hints here. Maybe one of those hints ask that. But yeah, sometimes you know they don't give you enough information, and you're like, well, I need a little bit more, and that's great. They want you to ask that question, so go ahead and ask them, right? If something is unclear, write code to remove duplicates from an unsorted linked list. So we have duplicate values. What does that mean? Well, let's say the value here is A, B, A, C. Our duplicate here is A. So there's two things about it. One is that we need to know that it has happened twice. And then we need to delete one of them, right? So that's two different things. There's deletion and there's duplication detection, right? Let's start with duplication detection. Okay, so how would we detect this? Well, the follow-up says, what if you couldn't use a temporary buffer? And what came to my mind anyways was like, okay, well, we basically need to keep track of if something has shown up or not. And one way to do that is to use just a simple little hash map. A true, B. So, and then we started A, we're iterating down the linked list. We're like, okay, B's here. Then we take a look and we see, oh, we're over here at A again. We're like, oh, A already exists. Okay, now we should probably delete it. I would delete it as soon as you found it. How would you do that? Well, we have previous now. So you could do something like this. So say you're at in to represent where you are now. The current node is in. So I would say something like in.previous, that is B, right? That is B. Let me do this in purple. So in.previous is B. Okay, we have that. So in.previous dot next, oops, let me, dot next equals, how do we access C here, right? We say something crazy like in.next, right? That's it. So in.previous.next equals in.next. Isn't that a wild statement to think about? But when you draw it out in a diagram, it makes perfect sense. You're like, okay, I'm here at N, I'm here at A. I want to get the previous linked list item node, and I want to set its next value to my to in.next. So in is always here, right? And in.next is C. All right, so I'm going to set in.previous.next to in.next, right? Very cool. So that's why doubly linked lists are a lot simpler to use, and it's just so much quicker, right? Because you kind of have the references you need to pull everything off. There we go. So in.previous.next equals in.next. This is how we're going to delete things. And look at how haphazardly I've done this so far, right? Delete node. Cool. When you're approaching interviews, you don't dive into the code. I have not dived into the code at all. I've just kind of thrown a bunch of stuff up on the page, right? And I'm not doing this to teach you. This is literally how I would approach this, right? I'm still doing this for my benefit, but this is how I approach things. Okay, so let's go back to it. So that's pretty much it. I think that's it. We just keep track of, has it appeared before? And then we move on. Now, let's talk a little bit about this weird hash map I've got going on. A is true, B is true, J, what the heck? This is the old way of doing a set, right? So there's this data structure in JavaScript called a set. It's wonderful, and I highly recommend looking it up on javascript.info. I would probably use a set here if I remembered the syntax super well, but frankly, I don't. Actually, screw it. Let's just look it up on javascript.info real quick. And you know what? I could implement this. I could implement this really quickly. I could totally do that. But maybe I should leave that up to you all. Okay, so javascript.info. Let's get out of here. Let's take a look at sets. There's a really good search function here. Set, search, and map and set. Look at that, map and set. Cool. Map is really cool too. I love maps because they can hold references to objects, and you can get things from it by the reference of it. And if all of that sounded like Greek to you, then look it up, right? Look it up some other time on your own. Let's go to set. Oh, they have a nice little navigation over here. Okay, so you have a new set. You can set.add, set.has. That's all we need. We just need set.add and set.has. Very cool. So if I were to do this, how about it? How about I implement this one for you? I'm only going to do this one because it seems kind of straightforward. Class node. And I'm only going to do this once because I'm just going to end up having a bunch of node objects that I keep having to redo again and again. So consider yourself lucky, I guess. This.val equals val. Cool. And we are going to, what are we going to do? We are going to, add next val. What are we going to do here? We're going to do this.next equals new node val. And here's what we're going to do also. We are going to say this.next.prev equals this. Oh my God, what did I just do? That's insane. It's not that insane. I'll show you soon. I think that's all we have to do there. And then, yeah, I think that's all I want to do. This is not append to tail, is it? No, it's totally not. This is add node. A.add next 2. A.next.add next 3. A.next dot. You can see how this gets annoying and kind of stupid. And append to tail is certainly the way to go. But since we are doing this so lazily, it's fine. A.next. Look at that. What do we know? Now look at that. We had the previous node in there, right? The previous one is 1. So we have our doubly linked list. Look at that. Very simple. And you see how I just kind of made up my own way of doing it, right? It's the concept that matters. The way you approach it does not matter as long as you nail the concept. Okay, so what do we have here? We have function remove dups, and we're going to say linked list, and we're just going to say LL. Yeah, screw it, LL. Don't call it LL in an interview. They'll be like, okay, that's lazy naming. You're a terrible namer. Okay, so we have this linked list, LL. All right, you know what? Let's just say node. Let's just say node because it'll be the starting node, right? And okay, so what are we going to do? Well, we were going to iterate through this linked list. So while node.next, cool. That's one way to iterate through it. And that's, I kind of like that way the most because, you know, it's going to stop when there's no next node. And I'm pretty sure, I am like pretty sure that we can just iterate through the entire linked list and be done with it. So what do we do here? So while node.next, let's say we have our set const, what is it? What should we call this set? Const vals equals new set. Cool. So while node.next, let's do vals. Oh, okay. If vals.has node.val, we are going to, oh, no, that's not what I wanted to do. I didn't want to press enter. This isn't a code editor, right? So I have to do, I have to hold, what am I holding down? I think I hold down shift enter. Yeah, the shift enter will prevent it from doing anything. Cool. Or prevent it from executing. But as soon as I press regular enter, it's done. It just executes. And I'm like, oh God. Okay, if it does, we're going to delete node. How did we do that? I'm looking back at my notes. And I basically said node.prev.next equals node.next. Look at that. I looked at my notes to do this. And frankly, that's not a small thing to keep in mind. This is how I code in general. I usually write it down before coding it. If you combine coding and thinking at the same time, it sucks. Do your thinking before you do your coding. That is the real trick of the day, or tip of the day, whatever. Okay, so I think that does it. Now here's the thing. Yeah, you're only going to get a duplicate. Yeah. This totally works. This totally works because there's no previous node on your first node, but you're never going to have a duplicate for your first node, right? So we're fine here. Okay, if vals.has node val node.previous.next equals node.next. Okay, we've deleted our current node, so we need to say after this, we need to say node equals node.next. And I think that's fine. I'm not entirely sure. So we will try that out. Otherwise, actually, we have to do this anyway. So let's just do this. We have to do this whether we have to iterate to the next node, whether or not it's a duplicate. And so that's pretty cool. Let's do Let's do else here though, just to say vals dot, what is it here? Let's take a look back again at javascript.info. Dot add, nice, okay. Now, will you, during the middle of an interview, be able to ask questions on syntax? And the answer is maybe. I have done it before. and sometimes they're forgiving, right? Other times they're like, you should know that. And but I remember an interview where they had me do something, and they're like, yeah, we'll tell you how map works, or no, it's how some syntax. I forget what it was. Anyways, here we are. I think this does it. I'm going to be a little crazy and just try it out. So we have, let me see, next. I want to, next equals new node. We're going to do a duplicate value here. So let's see. Oh, and you're like, Jay, what, you just added it manually? Yeah. And the problem with that was I totally messed up. This node no longer has a previous node, but you can do it that way, but don't do it that way. Let's do .add next, and we're going to do 2, right? So now our next node has a previous node, right? Very cool. Okay, so now we're going to remove dupes on this. So let's call it remove dupes. Here's the God, I hope that worked. A.next. Now look, I'm taking a look down here to see if the value is still there, and it's just auto completing for me. Oh no, it didn't do it. It didn't do it. Why didn't it do it? Oh goodness. I don't know. Why didn't it do it? Okay, I think the reason it didn't do it, if we look at how we did this here, right? We say node.previous.next equals node.next. Actually, I'm going to do a couple things to debug this. I'm going to do a couple things. I'm going to do a console log. I'm going to do a console log, and I'm going to figure this out, right? So here I am. I'm in super practice mode. I'm doing this live, and something went wrong. And this is what I do when I'm practicing. And I'm like, oh, something didn't come out the way I thought it would. We're going to console.log whenever it has it. And we're going to figure this out together. Okay, so it never hit. Oh my God, why did it not hit? That's interesting. Let's see. Why wouldn't it hit? What is vals while we are going through this function? I want to know. So while it's doing node.next, let's do console.log. Let's do 2 things. We're going to do node, we're going to do vals, and that should be fun. So let's check this out. Move dupes A. Okay, so it's going through everything. The set is building up, and then it doesn't hit number 2. Huh? Wait, did this work? A.next is 4. Okay. Next is 5. 5's next is 2, but it didn't hit it. Huh? That's interesting. Why would it not do that? Okay, so this is okay. .val, we're at 4 here. All right, let's do .next again. Right, .next. What the heck? What the heck? But over here in the console.log, we never hit that 2. That must mean that our loop, oh, no, look at our loop. What do we do wrong, Jay? Oh my God. So look at this, wild node.next. Dumb, very dumb. Why? Because the final node doesn't have a next. Oh, yikes. We want this when the node no longer exists. Okay, silly me. Failed the interview. Remove dupes A. Oh, and now val is not defined. Very cool. Why is val not defined? That's because the node no longer exists. I thought this would work. So we went all the way here to 2, and then let's see what's going on here. So A.next. Okay, so it didn't delete it because val is not defined. Where did I go wrong? Take a look. Right here in my console.log, I have this val thing and it does not exist. It is a part of Node. So my console.log failed me, right? Very fun. There we go. There we go. Oh my gosh. Okay, a.next.next.next.next. And now next is undefined. Look at that. We have done it. We have done it. Look at this. Oh my God. So you get to see my full practice suite where I implement this, fail, debug what went wrong, and then I learned something at the end of the day. And that is to be careful with your edge cases. When you're doing your loops, you got to make sure your fail case, your false case, where it kills the loop is appropriate. And what else did I learn? Be careful when referencing variables that don't exist. Very cool. These are all things, you know, when I usually, the first time I did this, I ran into all kinds of problems. And every time you run into a problem, write it down somewhere in a book. Write it down like physically. And the thing I would write down today is check your edge cases, check your false cases and loops, and make sure your variables actually exist and aren't attached to something. But we did it. We made it through it. So on to the next question. All right, let's go to share my iPad now. Okay, and is it sharing? Come on. There we go. Okay, so we're moving on to 2.2. This one's fun. Return kth to the last. All right, so implement an algorithm to find the kth to last element of a singly linked list. What do they mean by kth to last? They mean like they're going to give you something, a number, and they want you to find the k equals that number, right? So we have this linked list. All right. Cool. And we want to find a k to the last one. They're like, k is this, k is third to last, three to last. So this is the third to last one, right? Cool. So that's nice. Is it a singly linked list or a doubly? Singly linked list. It actually it's a singly linked list. It actually specifies that it's singly linked. And so that poses an interesting problem. So that problem is that if we're iterating down this singly linked list, 1, 2, 3, 4, we reach the end of the list. We cannot go back up to find the third to last one. That is really something. So what techniques do we have available to us? And this goes back to what we were talking about earlier with the double pointer technique. So let's go back to our reds and our purples. And they all start at the base node, right? So this one, I just happen to know the trick here, and that's okay. I think that, you know, you can pause here and try to think about it. If you're here live, that's okay too. But if you're watching this, try to pause and think about it. How would you use the runner technique to solve this problem? Check out the hints that they give. Try doing it on your own. You can even play around on the console, but you know, try to figure it out on your own. Okay, but I'm going to do it live anyways. Let me sip my coffee. All right, we're going to dive into this. So what is the trick to this with the double runner technique? Well, let me pose something to you. So the double runner technique is like one of them is slower than the other. So interesting. All right, we have a kth to last, and we want something to run slower than it. Well, how much slower should the node be? That's interesting. That's interesting. So let's say, what the ideal here is that this purple guy on his fourth run is going to be here. And then the whatever run, the red guy is going to be here. And that one is going to be our kth to last. We want to recreate this scenario so that we can say, okay, this is the kth to last because this pointer is here right now. That's what we're aiming for. How do we get there? How do we get there? Well, the thing is, we got to iterate that much more slowly. And so basically what's going to happen is we're not going to iterate red until we've gone 3 times, k times, right? That way, when it starts to be dragged along and we can't go any further with the purple pointer, we're going to be stuck at the kth to last, in this case, the 3rd to last item. So what does that look like? Okay, so purple, we're going to iterate it once, we're going to iterate it again. And now we have reached k times. Now that we have reached k times, we want to start dragging along. So we're going to go 4. And this is going to be the second time that, it's going to be the second time. It's going to be the second iteration for red, right? And now, since this is such a short one, we're at the end here, and the answer is right here. We've landed on it, right? That's so simple and straightforward. So what would that look like in the code? Well, I'm going to draw it out this time, just so we don't run into the myriad of mistakes I ran into last time. And it's going to look a little bit like this. So we're going to say we're going to have function k2 last. And we're going to take in a node, the base node, and we're going to take in k, right? That's our signature there. And what we're going to say is, okay, well, we have node. So let's have, we have our node right here. So while node, look at this, while node, we're going to iterate, but we're going to keep track of it in a particular way. We're going to keep track of k. So we have k already. Very nice. We're going to use that to, we're going to keep track of that. We're going to say while node, what should we set up? I want basically something that says a current node equals node.next. Oh, no, sorry. We're going to use node for that, actually. I'm going to use node for that. 1 second. Yeah, we're going to use node for that. And what we're going to have is we're going to have purple be node, right? Oops, sorry there. We're going to have purple be the node, and we're going to set up another node for k. So we're going to have k node. So let's do that. K node. And we're going to set that equal to node as well at first, right? Okay, so while node, what do we want to do? We want to decrement k until it's 0. So we're going to do node equals node.next. We're going to say k minus equals 1. If k equals, oh, no, less than or equal to 0. This is one way of doing it. You could also do it to where maybe we check if k is 0 before decrementing it. But here I'm just going to be lazy. So k is less than or equal to 0. If k is less than or equal to 0, then we want to say k node equals k node dot next. Look at that. Okay, and so what have we done here? We basically looped exactly what we're looking for. We're saying purple is here. Purple is this guy, and it's going to do node.next, and then we're going to subtract k. So if k was 3, now the first time we go to it, all right, k is 2 now. If k is less than or equal to 0, we start moving k node. It's not 0 yet. And so we're going to loop again. Node is going to equal node.next. K is going to go down to 1. And it's still not there. So we're going to go node equals node.next, k is 0. Now we're there. Now we start bringing k node along for the ride, right? And then once node is undefined, right? That is when, that's when this while loop will terminate. And so at the very end, we return k node. That's after this while loop, right? We return k node, and then the function ends, and that's it. That's all there is to it. So that's super simple. Now, I'm not going to test this in the Chrome DevTools. You can go ahead and do that. I'm sure the problems might arise around here. Like if this doesn't work, the problem is here because maybe I started dragging along this guy a little too early. So I would test this on your end, but this is basically how I would solve it. And that's kind of a simpler one. All right. It is 10 o'clock. I'm going to take another 5-minute break, and then we'll get started on 2.3. So I'm going to stop sharing here. I'm going to pause the recording. Set your timers for 5 minutes. It's 10:02, so that'll be 10:07 for me. So I'm going to pause and I'll be right back. Welcome back, everybody. I hope you took a 5-minute break yourself. Get up, stretch. This stuff is tough. All right, Nicholas asked in the questions, if you're asked a question where you need to select a data structure of your choosing, and you've memorized the time complexity for the methods relevant to solving the problem, how many different data structures is someone expected to know? There's some abstract data structures implemented using primitive data structures in a given language, but there's hundreds of data structures and algorithms on Wikipedia. What's the scope you're expected to know in a web dev tech interview? That is a fantastic question. There is actually a good little piece on this somewhere in this book where it's like, hey, get to know the things in this particular table. And then you will probably be fine 90% of the time. I think, honestly, the stuff they cover in all the chapters I found it. The stuff they cover in the chapters is basically what I have seen in every tech interview I've done. I've been doing it for 7 years in San Francisco. They're super competitive. They love their freaking tech interviews. And so I've seen a lot of stuff. Now, the table in question is on page 61. And it's in the technical questions chapter. And I really recommend all of you listening right now or just here live or in the recording, whatever, read that whole chapter. That really helps you come up with your own way of thinking algorithmically. But it also has this nice table. It's like, hey, here's some data structures, algorithms, and concepts you'll come across. Linked lists, trees, tries, graphs, stacks and queues, heaps, vectors / array lists, that's a Java thing, hash tables, what we did last time, algorithms, breadth first search, depth first search, binary search, merge sort, quick sort, very good stuff. I've had students get asked merge sort, so don't skimp out. Concepts, bit manipulation, no, don't worry about that. Memory, stack versus heap, probably not going to come across it. Recursion, a little bit. Dynamic programming, kind of related to recursion, and we'll go across that too. Big O, time and space, yes, learn it. But take a look at that table, and what I like to do is make sure I can do binary search by memory. I like to practice merge sort. I don't really get asked anything about quick sort. Breadth first search will come very naturally to you. In fact, we're covering breadth first search not in a couple of days, but on the 4th day, because that's the 4th chapter. Stacks and queues are the next one that we go over. They're really handy to know. And then we have heaps. I've been asked a question that needed a min heap or something like that. So it's good to know about them, but that was for his senior job. You might not encounter that unless you're also going in for a more experienced job. Hash tables are what we went over yesterday. Yeah, I mean, you live and breathe them, right? So those are the ones to know. Now there's hundreds on Wikipedia, and here's how you should approach those. Don't don't worry about them. These will take you all the way that you need to go. And if you end up needing more advanced data structures and algorithms, and I've done some more advanced stuff with them with graphs, frankly, just knowing how to work with them is even better than knowing all the ones that are out there. There's so many variations of graphs, trees, and how to balance trees, do all this stuff. Don't worry about them until you need them, right? And frankly, you're not going to need much beyond the scope of this book, so you're okay. Cool. All right, let's dive back in. I'm going to do, I think it's delete middle node. Let me, yeah. All right, I'm going to start sharing my iPad. Okay. Oh, this old song and dance. All right, put my keyboard down. There we go, a little bit more coffee. Awesome, let's dive in. Delete middle node. Implement an algorithm to delete a node in the middle, any node but the first and last node, not exactly necessarily the middle, because if it's an even number, what is the middle, right? It's a singly linked list and you're given only access to that node. What? Oh, implement it. Oh, oh no. Does that mean we're only given access to the middle node? Okay, implement an algorithm to delete a node in the middle of a singly linked list, given only access to that middle node. Great. Input. Oh yeah. So it gives you an example. It says the input. So let's take a look at this. I use boxes. They just went ahead and skipped to letters. Well, look at how much better that is. D, E, F. So an interviewer might give you an example and they might not. And if they don't, you come up with the example yourself, or you're shooting yourself in the foot. So come up with it or follow along to the one they get. Now it says the input is this node C. So result, nothing is returned, but the new linked list looks like A, B, D, E, F. Great. Okay, fantastic. So I'm already stumped. Let's see how I might solve this. So we're given C, and obviously, okay, I got a little insight here. This is cool. So we're given C. We obviously can't reference B ever. It's beyond possible to access B. So we just need to find a way to put D where C is. Now I have an idea, and I think I remember this being the way, quote unquote, to do it. But go ahead and pause if you don't have that thought in your head that maybe it'll work. Pause, try to work it on your own. Try to fiddle around with your diagram a little bit and look at it and try to come up with an answer based off that. Right? You don't need to write code to figure this out. You could try it, but you don't have to. So, okay, I'm going to dive into what I kind of remember is the answer. So we have C here and we have D here, right? Now we can't just set B.next equal to D. So what I'm going to do instead is make C equal to D. If that makes sense. I'm going to say C.next equals D.next and C.val equals D.val. Boom. What does that do? That turns C into D, and then D just, the original D just disappears. Oopsie poopsie. Good Lord. Oh my God. Oh, no, okay. Awesome. And then the original D just disappears entirely. Sorry, that thing jumped a lot there. There we go. D just disappears, the original one, right? It's no longer pointed to. And so this C one just sucks it in, subsumes it. That's really easy. So I'm going to do that. So function delete middle node. And then what I'm going to say is node.next. No, let's change the value first, just in case references don't work out. Node.val equals node.next.val. Node.next equals node.next.next. Boom, done. Is that the answer? I'm pretty sure that's the answer. I could code that up, but try that out on your own, and I'm pretty confident that's the answer. It might not be though. Try it out on your end. We're going to move on to a different question. I think that solves it. Oh, you know what? I'm tempted to just do it live. Let's do it live. I'll share my screen here. Desktop 1. Here we are. We already have a node. Yay. Okay, let's do A. Oh, come on. There we go. Oh, caps lock. A equals new node 1. Right, so, okay, cool. A dot add next 2. A dot next dot add next 3. A dot next. Don't you just wish I implemented tail? Add to tail, right? Add next 5. Cool. So the middle one is 3. A.next.next. That one is 3. We're going to pass that into our function. So we're going to say mid equals A.next.next. Cool. And we have this function delete middle. I'm take a node. Cool. And we're just going to say node.val equals node.next.val. Node.next equals node.next.next. And we're just going to hope that it totally totally works. So, okay, cool. A.next.next. Oh, we did it. We did it. Look at that, suckers. I did that. Oh my God. Look at me now. Okay. A.next. Let's dive in. Next. Oh, look at that. The next one's 4. The next one's 5. I'm a genius. No, no, I knew the answer to that one from memory. So, but I do like for things to go smoothly every now and then, and that went really smooth. Yay. But as you can see, doesn't always work out that smoothly, and that's okay. In fact, you know, sometimes in an interview, I'm like, oh, yay, they're asking a question that I can answer, and it just feels like luck. So don't get discouraged if you're like, oh my God, I've done all this practicing, but at the end of the day, you know, sometimes you just get lucky and you get asked a question that you just ace. And that only comes with preparation, right? I've been preparing for, God, how many times? Oh my God, I think I've really strongly prepped about 4 or 5 times for various technical interview phases of my life. Yeah, so I've done a lot of practicing before this. Cool. Humble brag, right? Awesome. So 2.4, partition. Little backstretch. Okay, write code to partition a linked list around a value X such that all, I can already tell that I'm going to need an example to understand this. Write code to partition a linked list around a value X such that all nodes less than X come before all nodes greater than or equal to X. If X is contained within the list, the values of X only need to be right after the elements less than X. I'm just reading this. I'm not understanding a single thing. The partition element X can appear anywhere in the right partition. It does not need to appear between the left and right partitions. Cool. So I hope you have your books because I'm not going to type that out for you. And that was really hard to follow along with. And this can happen in an interview sometimes when they're like, hey, do all this, blah, 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 blah. And I'm like, it's like, sorry, I zoned out in the middle of you saying that because I was trying to grasp what you said in the first sentence. And that's totally fine. Now we have the question here to reference. We can reread it, but in an interview, hopefully they've like made it kind of easier for you to understand the question. But as an interviewer, if I was interviewing you with this question, I'd be like, okay, I totally expect them to be like, oh, you have some examples, or like, I'm not fully clear on what that means. And they'll be like, that's okay. I word vomited on you. So don't be afraid to ask questions for understanding and clarity in an interview. They may even be, they are frankly expecting it. They do not want a robot that takes input and gives algorithm output. We've actually had brilliant candidates down the line who have answered questions and they didn't even say a word. And what do? What does everyone do? They fail them. They fail them for perfectly passing an interview. Why? Because they did not communicate. And so we had no idea what was going on. And in the real world, you know, we need discussion to figure out these technical problems, right? So it's really important. Now that's enough spieling. Let's go into the example. Maybe it'll start making sense with the example. 3, 5, 8, 10, 2, 1. And the partition, that's how I like to remember partition. A partition is like you part it out. So the partition is 5. And says write code to partition a linked list around a value X. So we're doing the partition around the value 5, such that all nodes less than X come before all nodes greater than or equal to X. What? So the output in, out, the output is this 3, 1, 2, and then 10, 5, 5, 8. What? Okay, so I guess the partition is going to be a new node. Let's read deeper into this. So partition a linked list around the value X, 5, such that all nodes less than 5. All nodes less than 5. What are those? I'm going to start diagram. What are all the nodes less than 5? We have 3, we have 2, we have 1. Okay. All nodes less than 5. All nodes less than 5 come before all nodes greater than or equal to 5. So 3, 5, 2, and 1 come to all nodes greater than or equal to the partition. So 5, 8, and 10. So that's what we have here. Oh, thank God. Okay, so diagramming saves the day again. This is it. You know, diagramming isn't like, you know, you're a scientist and you're trying to come up with a blueprint for, I don't know what, I'm mixing metaphors. But it's here where you're just circling stuff and you're just hanging on for dear life. Okay, so we have 3, 1, and 2. Oops, sorry, let's be color. Let's keep our colors consistent. We have 3, 1, and 2 in the output. And then we have 10, 5, 5, 8. Now notice these are not in any particular sorted order. The only thing that matters is that this partition 5, you know, there's a left side and a right side. So the partition element X, as it says, can appear anywhere in the right partition. It does not need to appear between the left and right partitions. So it doesn't have to be in the middle of the 2 partitions, right? It could be wherever. And why is that helpful? We'll probably find out. So if X is contained within the list, okay, this is interesting. If X is contained within the list, the values of X only need to be after the elements less than X. What? The values of X only need to be right after the elements less than X. So, okay, so it's basically saying that if the partition number is also already present in the linked list, then this number 5 here can appear on the right side. I think that's what it's saying, right? So cool. I just spent 4 or 5 minutes understanding the question. And this is great because I would have had that conversation I just had out loud to you with the interviewer. And then when I'm like, oh, okay, I get exactly what's going on. That's when I start thinking about what the code would start to look like. A lot of people dive into the code and I'm like, stop, right there. Do not do that. Figure out the question first, get your examples right, and then start thinking about how you would structure the code. Don't even start the coding yet. Start like mocking the code out and doing some examples of how you think this might work. Okay, that's enough spieling. So I know how the input turns into the output. What I don't know is literally anything else. So let's figure out how to do this. So is this a singly linked list? It doesn't say. Okay. Yeah, no, it doesn't say at all. I'm going to go ahead and assume that it's not then. That's an assumption. And I would check that assumption with the interviewer as always. And he'll either say yes or no. But I'm going to pretend he said yes. Okay. So the partition is 5. And we have this, we have all these circles and they're so annoying, aren't they? Let me just get rid of them. Nice. So we have this over here. I'm going to stick with purple. Yeah, this linked list. Now, obviously, we're going to need to iterate through it. This is a doubly linked list. Oh, actually, look, the example is a singly linked list. Oh my gosh, I'm so sorry. It does say of a singly. Oh no, I'm so stupid. I was looking at delete middle node. How dumb. Let me look back again though. No. Okay, so this could totally be a doubly linked list, and we're going to assume as much. You know what? Why am I doing it that way? Just add the arrow. There. Cool. Maybe that'll help me iterate. Maybe I don't even need that. So we have the partition, and do we have to modify this, or do we get to create a brand new one? Interesting. So there are 2 ways I could do this. One is which I create a brand new linked list, and I just do it according to the rules that we have. Or I can modify the current linked list. That would be interesting. I think what I want to do is, I think I want to modify the current one. I think I do. Why? Well, if you create a new one, that's extra space complexity, right? So we end up with 2. Maybe the first one dies, but I think what they want to do is to just keep the original one up. And I would ask my interviewer that, I'd be like, do you want to keep it? And let's just pretend he says yes. Do I know that as a fact? No, I don't. But I'm going to assume he said yes here. So what would we do? Well, we need to iterate through this linked list, right? So we're starting here. I'm going to use in to indicate the current node. Per node. All right, why not write the whole thing out? So I'm starting it in, and I have the partition is 5, right? So what I'm going to do, I'm going to compare things. I'm going to have a left partition and a right partition. And I think what I want to do is keep track of which node is at the tail end of the left partition and which node is at the tail end of the right partition. That's brilliant. Okay, keep track of things. Boom. Awesome. I like that. That's write this down. Keep track of things. Look at that. With an object. With an object. Or not. Or with a var. Like const or let. Like const or let. Look at this horrible note, right? Like keep track of things with an object or not, or with a var, or with const or like, whatever, or const or let. Okay, but that's helpful. That adds context, kind of makes it a little funny for me at least. Okay, so we have the current node in, and I want to keep track of right partition tail and left partition tail. Oh, I like this already. Okay, so these are going to be nodes, right? Actually, all of these are going to be nodes. Cool. And we're starting at 3. So let's start at 3. We're over here at 3. We're going to say while, what did we learn? While node. Right, and the function will take in node. I'm just going to start with the while loop here. While node. So if, what are we going to do? If node.val is less than partition number, it's less than partition. I'm gonna abbreviate partition as P. Now, I would literally tell the interviewer that. I'll be like, hey, can I use P instead of writing out partition? I'll be like, yeah, sure. So if node.val is less than P.val. Oh, no. P is not a node. P is just the number partition. Look at that. I was already confused with my own naming. Good Lord. So P is 5 right here. So if it is less than that, then we're gonna say left partition. What are we gonna do here? Actually, what we want to do is we either want to, so 3 is in a very cozy location where it's already in the left partition. Left partition tail, let's say left partition tail actually equals the original node. Right, that's currently it. But here's actually, no, it's not, is it? Because if it was 7 at the very start here, we had 7, then it's in the right partition node. So it's not. We don't want to say that at all. Cool. Good catch. Look at that. I used my examples to invalidate code that I was about to write. That's when you want to invalidate your own code, and you want to do it through examples. So here's a cool another note. Come up with examples that invalidate your code. Cool. Write that down yourself. I hope you all do that, because that is the key to not getting a question wrong, is to come up with examples that invalidate your code. Okay, cool. Anyway, so left partition equals node. Oh wait, if there is no left partition, there's two situations here, right? So if not left partition tail Left partition tail equals node. Nice. I like that. And then, but here's the problem. Here's the problem, right? Now we want, if we're in this case where 7 is the first one, and then we hit this 3, we want this left partition tail to be the very front. How do we do that? How do we do that? That's an interesting thought. That's a very interesting thought. And I kind of want to tackle that right now while my brain is not fried, because we've been here for an hour and a half and my brain, I know, is approaching danger zone, right? So let's take a look at this. Let's go back to our diagram. Let's go back to our diagram. Okay, cool. Nice. Nice little eraser function there. I'm going to make that a little cleaner for me. 7. Cool. So we're here at 3. And let's even say there's an 8 here. All right, we're here at 3 now. And this is the first time that the partition value is greater than the node that we're at. Well, there's a few things about this. One is maybe I could send all the right partition stuff all the way to the front and just say, screw it, send that sucker to the very tail end of the entire linked list, right? That could be something. And that way it slowly builds up over time. And I don't have to mess with it. Ooh, I kind of like that. Let's just say if we see a right partition node, we just send it all the way to the front. If we see a left partition node, we send it all the way to the back. Oh, I like that. I like that. We could do that. Or, we could send it all the way to the back the first time, and then the next time it comes up, attach it to the tail. That's interesting too. Do I like that? Maybe. Now, my approach might be different than someone else's approach here, but maybe that could work. And I kind of like it. Let's see, let me think. So let's think of the differences between throwing it at the tail end and attaching it to the partition, right? So if I attach it to the partition, I have to go to this partition and insert it here without destroying the linked list, right? So here we are, we're at 3. I don't want to destroy the linked list, so I'll keep it there. I'll just keep it there. But let's say right after the 3 was a 2 instead of this 5. Right. Let's say it was a 2. So I've modified my example. So let's say it's a 2, and I would, oh no, that's not a great example. Let's say the next one is 8, and the next one is 2. You know what is funny is why that example wasn't good. I was like, well, it's already in the right spot. And that's funny because what I'm going to do is that when I see this 8, I'm going to send it to the tail. And then what happens? Well, I see a 2 and I don't do anything. Oh my goodness. Hey, that could be the insight I'm looking for, right? Then I see a 10, I move the 10 to the very front. And then I see a 2, I don't do anything with it. Oh, look at that. I'm just appending values greater than the partition to the very end of the linked list. And then I don't have any problems, because naturally what will occur is that these will sneak their way to the front. And then when I get to the very end of the linked list, and that's interesting. I have to know when I'm done, right? I have to know when I finally reached my Zen here. But essentially, when I get to this 1, everything to the right of it is going to be greater than the 1, and I will have successfully partitioned everything. I'm not even keeping track of the left partition tail. I'm just, or a right partition tail. I'm just throwing stuff to the right if it's greater than the partition. So I just need to keep track of the very tail end of the linked list. Look at that. So interesting. Okay, cool. So let's change our entire approach. Yay. Okay, awesome. Isn't that something? Like, I came up with an entire thought process and then invalidated it on the spot with examples. Cool. just like I said, come up with examples that invalidate your code. And I guess we did that here. Why not? So, okay, that was a little interesting. So while node, okay, if node.val is greater than or equal to, because you remember, go back to the question. The question says, before all nodes greater than or equal to x, right? All nodes less than x come before all nodes greater than or equal to x. So greater than, if node.val is greater than or equal to p, the partition, what do? Send it to the end. Why did I put end in quotes? Well, because all of a sudden the end is going to be changing, right? There are two ends that I'm worried about here. I'm worried about the end of the original linked list, but when I start adding to it and there's all these nodes attached to it, let me draw that. Once I have moved 8 and 7 over here, it is now linked to, actually, let me delete some stuff so I have some space here. It is now linked to here. So I sent 8 over, and then I sent 7 over. And then and now this is the new end, right? But this is the original end. And I want to know when I get to the original end that's when I stop iterating, but I could keep going forever, right? So, well, not forever. I could probably stick to a point where I'm like, okay, because I would keep sending that to the right. I'm like, oh, that's greater than the partition. I'll just send it to the end. So I want to keep track of the absolute end, or no, I'm sorry, I want to keep track of the original end. And then I want to keep track of the absolute end, because the absolute end of the list is where I want to append things to. So the next one up would be 8. I want to keep track of this now and then say, okay, well, the next one's 10, cool. But then my original iterator is going like, okay, I did 8, I did 2, I did 10, I did 2, I did 1. 1 is the original end. And so now I want to stop iterating. And I want to make sure that my other partition joins in, because it tells me to add the partition to the linked list. Okay, nice. So when I say send it to the end, well, which end am I talking about? I'm talking about the absolute end here. So I want to keep track of that. So that's interesting. How would I keep track of where the very end is? Well, it looks like I'm going to have to iterate all the way to the end, because we start with a node, right? In our function signature, function, yada, yada, yada. We take in the node, bad spelling. We take in the node, we take in the partition. P. Oh, come on. There, not there, P. Right, so we take the starting node. And so one thing we want to find is the very tail end of the node, or at the very tail end of the linked list and the original end of the linked list. So let's just say, how should we do this? You know what I like doing? Let's make a function for this. Say const original end equals find tail node. What am I doing here? I'm taking that original node. I'm going to have this function find tail. It takes the node and says while node equals node dot next. Actually, while node dot next. This is funny. I actually want this to terminate when there's a node dot next, because if there isn't, then we're good and I can return that node. If we return node, if we just let this go on until node is undefined and I return undefined, then I haven't found the tail, I have found undefined. So we want to return it right when we're at the tail end of it. So that's going to return the tail node. Nice, find tail node. Cool, and now that really cleans up my function. Okay, const original end is find tail node. What else do we want to do here? I think maybe, I don't know. I'm going to come back to this const current end, current tail also equals, and we're just going to say original end. But I'm worried about the references there. So maybe not for this one. We're going to do find tail node. No, you know what? I kind of want to test this out. You know, this is where thank God I'm practicing, because I want to know if I do original end here and say something like current tail dot next, is that going to increment original end? I don't know. So I would want to test that out, you know, as practice on the Chrome Dev tools. I'm not going to do that since we only have 17 minutes left. All right, so send it to the end. What does that mean? We're going to say current. Well, first we got to delete. No. Current. Actually, yeah. Let's. How would we send this to the end? I think what we would do is we have the current tail, right, and that's the very end. Current tail dot next equals node. Node dot next equals undefined. What does that do? It sticks it at the very end and it removes this link from 8 to 7. Oh, that is so dirty. Let me erase. Oops, too much erasing. Right, so that's going to say, let's go over here. No, let's go even further. Okay, cool. That's going to say, okay, here's the current tail, number 1. And we're going to say its next is 8. And then, but 8 currently links to 7. So when we do this, this is actually going to be the loop currently, right? And we don't want that loop. So then we say this node's next is undefined, and that kills it. So this no longer exists here because it doesn't point to anything. So it effectively creates this tail end there. Very nice. Now, do we want this to be a doubly linked list? Well, the more I go through this, the more I realize we don't really need previous. So just to make things simple on me, I'm going to make this a singly linked list. So that'll make it simple. Okay, cool. So that's what we did here. We sent it to the end and we removed the previous next so that it didn't have that reference. Is this all I need to do? Well, node. Wow, is that all I need to do? Okay, so let's do it. So we let me remove some of these. Cool. All right. So we did that with 8. We'd have to do that with, I'm going to go to red here. So we did that at 8. Now that we're at 7, okay, then we send 7 over here. 1, we don't send 3. 3 stays. 8 moves. Oh, and look, when 8 moves, we need to delete it properly so that 3 now points to that 2. Okay. Interesting. Okay, so we need to do that as well. This is where my brain starts to peter out. Do I have any more coffee? Just a sip. Okay, so we need a function delete node or move node. Yeah, let's do that. A function move node that takes care of this situation for us so that we don't have to come up with that in our code. So function, I'm going to scroll down just a little bit. Function move node. And you know what I want now? I want my previous node back, right? So, okay. Move node is going to have to be more advanced so that it also sets the previous. So it'll be like node.previous equals current tail. Look at that. Cool. So we're going to have to add that in, but we're going to move this over to move node to front, or move node to tail. To tail. Oh, we're running out of space, but look at this. One node kind of sneaks on over here. Look at that. Nice. So first we need the tail, and then we need the node. What are we going to do? We're going to say tail.next equals node. We're basically going to take what we had. Oh my God, who's calling me right now? Nonprofit. I'm sorry. Okay, so sorry. Spam calls. Good Lord. And put your phone on silent during an interview. Yay. Tail.next equals, we're basically taking this whole thing over here and we're moving it over here. But I changed the naming. Tail.next equals node. Node.next equals undefined. Node.prev equals tail. Nice. That's how we're going to do it now. We got this nice function. We're going to send it to the end. We're going to say, and delete all this mess. I'm going to say, move node to tail. Now, the other thing we have to do though is we have to make sure the nodes around node are fixed first. So we only deleted them, right? We only moved it. We need to take care of the nodes around us. OneNote has this wonderful feature where I can just move stuff down. So take a look at this. Oh yeah, nice. So first we need to take care of surrounding nodes. How do we do that? So we're going to say node.prev, it's the same one from before, equals, node.prev.next equals node.next. There we go. This is the deletion operation from earlier. See how these questions build upon each other. Really nice. And then we say move node to tail. And so tail.next equals node. Node hasn't been garbage collected yet. Node.next is undefined. That's very good. Node.prev is tail. We did it. All right, we moved it to there and we took care of this situation right here, where we need to take care of the nodes around us when we move it. Awesome. And I did that inside a function. And the interviewer is going to be like, oh, how brilliant of you. You did a function. That's awesome. And that's really good. So that's good code quality. And that's good. That's some brownie points. Current tail and node. Abstract away complex things, just like we did with find tail. And that's a good lesson. Make a function when things get hairy. Things get hairy inside algorithm. But that's not it, is it? It's not just that it was hairy, it's that we could pull out that functionality, because this original function is about partition. So this is literally function partition. You know, and there's this concept called single responsibility principle, where, you know, we have this partition function, right? Is partitioning all about finding the tail? No, it's something we do inside of it. So break it out as a function. Is partitioning about moving the node to the tail? Well, that's something you do inside it, but it's not a part of it. So you can pull that out of a function. We're here to partition. I don't care how we partition. It's important to know, but you kind of want this thing where it's like, oh, okay, well, what we need to do now is move the node to tail. Let's break that out into function, because that's kind of complex. Now, you might not have to do that, but I find it really nice, and it kind of cleans it up a bit. And this is going to be a nice clean function at the very end in 9 minutes. And I'll open a Q&A after, by the way. But in the 9 minutes where there was a question in the thing, if you find X, then can't you just start iterating from the start of LL and place anything greater than X to the right of X? Yes, but here's the thing. It's not a, I'll come back to that question at the very end, because we're just about there, Nicholas. Sorry, that was a question in the comment. So let's go back to here. We've built our function out. It kind of makes it easier for us. We're saying if the node is greater than or equal to partition, move that node to the tail, do it safely, right? Nice. Okay, so I think that's it. So if, all right, let's come back here. Earlier we were like 8. Okay, now we've moved 8 and we've connected 2. So 8 is here, cool. Now we're at 2, 2 stays. We're at 10 now. 10 moves over here. And it's doubly linked, cool. And then we're at 2. 2 stays, right? Because that was how we moved it. And then we're at 1. 1 is done. And now we need the 5s. Where do we put the 5s? It doesn't matter. We can stick them at the end. I think there was a 5 earlier, but let's just say there isn't. And let's just say we saw the partition, so we have to add it to the end. There we go. Now this is partitioned because there is no 10 here. There is no 8 there. There's no 7 there. We're rightly partitioned now. I think this is all we need to do. So while node, the other thing we need to do though is terminate this while loop at the right time. And we could say while node does not equal original end. And then we're done. Then I think we're done. What it does not, I think that's it. I like this. And you know, we have some time left and I'm going to implement this. I'm going to see if this actually worked. And then we'll open to some questions. Sorry, Nicholas, if you got lost there. Sorry to anyone if they got lost there. That is frankly a more difficult question. But come back to it, you know. I've always been lost the first time I've done these questions. And then I come back and I'm a little less lost. And frankly, if you're doing this the first time, it might take 3 or 4 times before you are no longer lost. Sorry. Okay, we have this function partition. And look at me now. This is why I love writing code or pen and papering code before actually writing the code, because oh, we need to write find tail first. All right. Because now I'm just going to copy down what I've already written. And so I don't have to do any thinking while I'm typing, which, like I said earlier, don't think and type at the same time. I would write that down. Don't think and type at the same time. I'm writing that down on my iPad because I'm gonna post these learnings somewhere for you. Don't think and type at the same time. Maybe you can get away with it. Maybe you're like, oh, well, I can experiment better when I'm coding, and that's fine, but try to work your way to where you don't do that. Okay, function find tail. What was that all about? That was while node.next. Node equals node.next. Return node. Nice. Oh, capitalized node. Are you kidding me? Return node. Nice. There we go. Okay. We also have this function move node to tail, and we took in a tail and a node. All right. So what do we have now? Node. We have take care of surrounding nodes. Node.pre.next equals node.next. Cool. What else do we have? We have move node to tail. Tail.next equals node. Oh my goodness gracious. Okay. Then we had node.next equals undefined. We have node.prev equals tail. Nice. That's it. Cool. All right, let's go to partition. Oh, it's saying my internet connection is unstable. I'm going to repeat what just happened. So I made this function find tail. I made this function move node to tail. I did that before writing out the final partition function in this, because it's going to reference these prior 2 functions. So keep that in mind. Const original end equals find tail node. Const current tail equals original end. And what did I say earlier? I said I'm worried that if I do current tail.next, it's going to increment original end as well. And we're going to find out if that's true. We're going to find out if that's true or not. And I might do that by console.logging. But first, I'm just gonna YOLO it. While node does not equal original end. We're reaching 3 till, but I'm gonna also have a Q&A at the very end for y'all. So don't worry that we're coming up 3 till. It's just an arbitrary end time. If node.val greater than equal to p, 3. Send it to the end. Move node to tail. All right, tail, node. We're missing something. Current tail now equals current tail.next. It should have a yeah, it should have a thing after that. Nice. I forgot that when doing the when doing it on pen and paper, right? And I probably would have been docked for that because it wouldn't have worked. He might have said, "Oh, is something missing here?" And I'd have been like, "What? Nothing's missing." So be careful. Cover your ends there. Okay, cool. Current tail. I don't know. That's the node is make sure you've taken care of everything. Write that down, I guess. If node, I think that's all I had to it. Let's try it out. So let's create a new series of nodes. New node. 1. Oh boy, this is going to be. You know what I'm going to do? I'm going to recreate the input they've given me. So a equals new node 3. Oh, my hands are starting to hurt. That's not a good sign. Okay, a dot add next. They had 5. Okay. A dot next dot add next. They had a 8. A dot next dot add next. What did they have after 8? They had a 5. Next dot add next. They had a 10. We're almost done. Add a 2. A dot next dot add next. They had a 1. Okay, so this is 3, 5, 8, 5, 10, 2, 1. Cool. And that's the whole thing. That's a whole enchilada. So let's see if this works. Place your bets right now. Oh no, oh no, oh no, I broke something. Oh no, I bet it's still, what happened? It's not giving me my stuff. Can I even like, oh no, I broke it, crap. Hang on, I gotta copy these before they disappear forever. I bet that while loop never ended. Oh my goodness, oh no, I didn't set the node again. Oh no, refresh. It's running an infinite loop. I might even have to kill it. Oh my God. Okay, we have to kill this. It's running an infinite loop right now. Okay, cool. Oh my gosh. I gotta take care of my stuff. Okay. Node equals node dot next. Oh my God, I was not iterating the node up. Good Lord. Oh my God. Okay, let me remove these undefineds. Oh my gosh, what was I thinking? Now I have to recreate nodes. I'm so sorry. Oh, it looks like I don't have to recreate it that hard though. Nice. Okay. Do I get the other stuff? Yes, a equals new node 3. A dot next dot a dot add next 5. I don't have to type all this out. Thank God. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What did I just show you? My secret little trick of when you go right back up the thing and you have to figure out where, fuck it. Okay, anyway, so we have node 3, 5, 8, 5, 10, 2, 1. And that's all. Okay, and the partition is 5. Oh my God, I said you had to add the partition in, but you don't have to add the partition in. That was so dumb of me. Yeah, there were just 2 5s in there. Ridiculous. Okay, so you don't have to add it in, and I didn't add it in. That must have been confusing the entire time. I apologize. Okay, so let's try it now. Partition node 5. Node is not defined. Oh, okay. Assignment to constant variable. Oh my goodness. I know exactly what I did. I got a little brave and I was like, you know what I'm going to do? I'm going to make this a const when it should be a let. Because we changed current tail. Stupid. All right, let's do it now. Cannot read val of undefined. Oh, I did that too. I guarantee you I did that. Where's val? Where are you, val? Node.val. Is node undefined? Node might be undefined. I think that's the case. Oh goodness. I think original end changed. So let's do something here. Let's console.log original end. And then let's run partition A5 again. Look at that. It only did this once. Interesting. Why would that only console.log one time? We had find tail node. I bet that maybe that changed node. So what, let's see, but why would it pick 8? Next. Oh my God, look at that. It destroyed my entire thing. Oh my gosh, I did this so wrong. I did something terribly wrong. What did I do wrong? I have no idea. I bet it was something with, like as soon as it started, I screwed up. Node equals node.next. That wasn't it. I bet it's this move node to tail. I bet I did something destructive here. And I bet it has to do with this or something along these lines. So what I would do is console.log from here. Now I'm going to try to figure that out, but it's already 11. So I'm going to open the floor to questions real quick, actually, and then I'm going to come back to this. And if y'all want to leave, you can leave. If you want to stay and ask questions, I'm here to answer questions. And then I'm going to answer those and probably try to figure this out. And I'll keep recording that as well. We have 3 here. Does anybody have any questions? How did that go? I'm gonna wait for the chat.
Personally, I mostly followed that. I think I probably will stick around just to watch you finish that off. But
Yeah.
no, thank you for going through that. That was definitely a lot more complicated than an example.
Yeah, that was a complex one. I ended on a complex one last time, and I honestly didn't even finish it. So yeah, but that's cool. Stick around. Anyone else? Going once, going twice. How often do you use linked lists? In the real world, almost never. But that's why I might recommend only doing the first 4. Don't, or maybe even just the first 3, especially if this is your first interview. Do the first 3 and then go on to the next chapter. They build you up for the next chapter though. So just try to get them, try to understand them, and then take it from there. How often do I use it in the real world? 0. But I think I remember React's fiber implementation uses linked list, if I remember that correctly. So there are cases out there, but I generally never use them. Okay, I think everybody has asked a question that wants to ask a question. So let's go back to my failures. Okay, awesome. We're here. We have done something wrong. And I want to console log what that is. What's interesting is that I started out with A being something. Maybe I didn't even do A right. A.next is 8.next. Oh, this node has lost its next. Why? Because the previous node was not taken care of. And that probably had something to do with move node to tail. I think that's where it went wrong. Because look at this, the next is undefined. So that means A is pointing to 8, and it should not be pointing to 8. Right? It should be pointing to the tail. Maybe I did something wrong with the tail. Let's see what the current tail is. All right, over here. I'm going to say console.log tail node, and that's going to provide some value for me. Oh my goodness, it actually did it even call move node to tail? Huh, it just console log the original end. Then said no dot val greater than partition. Let me see if it even made it in there. Oopsie. Oh my gosh, it doesn't even go in there. Why wouldn't it do that? Let's see if it's even picking up my console logs. It is. Okay, so something is going terribly wrong here because no dot val greater than equal to P is not even hitting. And that is, oh, duh, A has already been destroyed. So, so we need to fix A real quick. Oh my God, we're just gonna do this. Oh my God, this is gonna be so annoying. Equals new node 3. I'm gonna try to do this in a less annoying way. A dot add next 5. I'm gonna see if I can do this. A dot next dot add next 8. Hang on, let me see if that worked. A dot next dot next. Nice. Okay, I'm gonna have this one long thing to set this up. Next dot add next 5. And then I'm gonna copy paste this. Oopsie. A dot next dot next dot next. Get rid of the dots here. Let's make this. There we go. That's a little easy to read. 10, 2. Then A dot next dot next dot next dot next dot next dot add next 1. Are you kidding me? Did I mess up? Where did I mess that up? 3, 4, 5. How did that not work? Oh. There we go. So what is A? 3, 5, 8, 5, 10, 2, 1, undefined. Cool. So very good, very good. Now we have built that up, and this thing is here when we screw up our thing again. So we got partition A5. Cannot read val of undefined. Awesome, but we got our highs back. That's cool. So we've done this at least a few times now. We've done this at least a few times now. How many times do we say hi? I should have said something different here, shouldn't I? I'm going to say hello here instead. And then A dot next dot next dot next. Okay, so now it's, you know what I bet? Wait, what? Interesting. It kind of did partition it. 2, 10. No, it didn't partition it at all. Didn't do it at all. Oops. Yeah, it didn't partition it. Or did it? I think 5 is at the end now. I don't know if that was the original plan. A dot next dot next dot next dot next dot next dot next was 1. So it did try partitioning. Look at that. It's 5 there and 1 here. So something happened. Let's do the partition again. So can't read val of undefined. So obviously, I think the node is what's being undefined. So it only says hello here. Interesting. So what did I console.log? I console.log the original end. Now the original end is this 1 number. And that's good. That's what we want. No, is that good? Yeah, that's the tail end. Yeah. 1 is the very final one. So we have our original end. We did that right. And what I would expect is for 5, 8, and 10 to be on the right side. And so it'd be like, yeah, it would have been sent to the right side. But instead, it looks like what we got is we are at A, 3, dot next is 8. So and dot next is 5, dot next is 10. We have the partitions on the wrong side. Oh, goodness. We totally messed up here. Or I totally messed up here. Let's see what's going on then. So we're here, and let's have some more informative console logs. How about that? Okay, so that's not informative. We know original end sticks to where it's supposed to. We know we say hello. Awesome, Jay. Awesome for saying hello there. Okay, let's console.log. Let's start node.val, and let's do p versus p, right? Just to have a nice comparison there. And then at the end of this, I want to see what the current tail is. Console.log current tail.val. We're going to say current tail, just to be informative for us. And then here, we're going to say which node we're on, console.log node.val. Cool. And then up here, we have moving node to tail. We're going to say tail. I'm going to say node. And then let's make sure we have our node previous right here. Then we're going to say node. We're going to put the node there so we can play around with it. All right, those are some informative console logs. And let's do our partition. Current tail 5. Awesome. So it's a current tail 5, and then it exploded. Let's see what that's all about. So current tail.value, and then it exploded. Why? Here, there is something undefined. Why is that? I wonder what, well, look here, moved. We go to moved, and we're given the node. The node's next is undefined. Interesting. So, okay, so we have node.val here. We go 3, 5, 5, 5. Interesting. Let me make a more informative console log real quick. Console.log. Current. Okay, node val. All right. And let's do this again. We're going to diagnose. You see how I diagnose things now? Okay, cool. So node val 3, node val 5. Then it just output 5 twice. Where do I do that? Where do I do that? I don't know. Node.val. Then here. I need to do a little bit more informative there as well. So let me change that function real quick. Node val. This is greater than achieved. Greater than or equal achieved. Cool. Nice. Okay, greater than equal to achieve 5, 5. They're equal. So it went 3, and then it went 5, and then it was like, okay, so we have 5. And so far, everything's playing great. Then moving node to tail. So the tail is 1 at this place. And then the new node is 5, right? That makes sense. Then it moved. Now look at this. The next one's fine. So the current tail, though, ended up being 5. That's fine. That's perfectly fine. Everything is fine. So why is it saying val is undefined? Huh. Which one? It's on line 24. Let's dive into where it's saying it's undefined. It's saying here, node.val is undefined right here. That's interesting. That is very interesting. I wonder why it's saying that. By the way, this debugger is really fantastic for debugging if you're doing your thing. Someone added in the chat, should it be greater than equal to? You're moving 5 to the end. Yeah, I moved 5 to the end because in the question it said before all nodes greater than or equal to 5 to x. So I want to move it to the end, I think, is to keep going there. Okay, and so let's take a look. We're here and says val, it fails here. Fails right there. That makes no sense, does it? So what is node? Let's get node before and after this. How about that? Let's rechange that here. Let's say, okay, we have console.log node orig node console.log node changed node. Node changed undefined. Why is that? That's because the node is the thing that got moved to the very, very end. Oh my God, what was I thinking? Of course, node.next can't be what I set it to. I need the original next one. Oh my goodness. Oh my goodness. Const original next equals node.next. And the node equals original next. Oh my God. This has actually been kind of fun though. I'm actually enjoying this. Son of a, okay, a.next.next.next. Oh no, but now it's not working at all. Now I have totally screwed the pooch. Let's check out A. A is 3. The next one should not be 8 or 5, which 10, and then undefined. I've completely gotten rid of all of the values less than 5, except for the original. Nasty. Why? I would have to say that my approach with moving did not actually bode well. So I moved this node, right? And something went wrong here. And I think that's the problem. And I think the problem might be here. I modified the node before sending it to the very end. And maybe that's something, but it is happening in move node to tail, I think. But we can look at we can look at our change logs up here. Now, node val 3, node val 5, node val 8. Yep, we're currently going the right place. Node val 5, that's true. Node val 10, that's true. Node val 2, and then node val 1 is the final one. So we stop. So it's done that right. But what happened? A moved. I think, is it A? A's next probably got moved in some way. And then something else moved it, and then something else moved it. So we had our function here. Node.pre.next equals node.next. Tail.next equals node. You know what? I got to tell you, my brain has totally blanked now. I have no idea what happened. What I might do from here, since this is going on for 20 minutes more than I planned, what I would do from here is look at the answer in the back of the book. Let's go take a look. It's on page 212. And let's look at this. Before start, before end, after start, after end. Oh, goodness. Yeah. New list. Oh, they did have one where they just start a new list. Oh, it's saying we can make a new list since the interviewer hasn't specified it. Oh my gosh, that would have made it so much easier. So ask the interviewer. I just made an assumption that made it so much harder on me. And then, yeah, take a look at the solution on page 212, and it goes over it. Wow. I'm going to have to add something in where I'm like, hey, I totally butcher this question, so heads up. But we're going to stop there. I'm going to stop sharing. This is where you just kind of have to go back to the solutions, figure it out from there, and redo your approach. Very fun, very fun. That's all for now. I'm going to stop recording. Thanks for sticking around if you saw all this.